Hello everyone. Today we're going to begin our discussion of functions. Okay, it turns out that nearly all the equations that we have to deal with are functions. So the properties of functions become very important to us. As a matter of fact, the whole rest of the course, I think all of the equations that we're going to talk about will be functions. So first of all, let's figure out what is a function now. Okay, a relation is a set of ordered pairs, which means now we're moving to where we have two variables, right? An x and a y. Think about all the equations we've talked about in this course up to this point. We've always said, oh, there's one variable in there. If we had more than one variable, we couldn't solve it. We could solve for the variable. But now we're going to have a set of ordered pairs, so two. So a function is a relation. So a function is a set of ordered pairs where every first component, there is exactly one. This right here is what makes it a function. Exactly one second component. Okay, so every first part of the ordered pair maps to, corresponds with, however you want to say it, exactly one value of the second pair. So the set of values of the first coordinate, that's the x, we call the domain. So the x's are called the domain. The set of all values of the dependent variable, or the second one, right, the y's, remember, are ordered pairs, take the form xy, is the range. Okay, so just to reiterate one more time, what makes something a function is that every x value corresponds to exactly one y value. Every x value goes to only one y value. Okay, so let's decide if some things are functions or not. Okay, so decide whether the relation defines a function and then give the domain and range. If I'm looking at just a set of ordered pairs, all I need to do really is look at the x values. As long as the x values are all different, it's going to be a function. So this thing, yes, is a function. Okay? Because, so look at this one. If my x values are the same, then I need to look, wait a minute, do they go to different y values? A 1, 1. Oh, I've got a 1 match to a 1, and then I've got a 1 match to a 2. This makes this not a function, right? That's what makes it not a function. So really, as long as all my x's are different, x is the same, excuse me. Let's see if they go to different y's. This one goes to a 1, that one goes to a 0. No. Okay, that's how I determine if a list of ordered pairs is a function. Now the domain is simply the x values. So 1, negative 2, 3 for this one, not negative 1. 1, negative 2, 3. And the range is the y values. So 2, 4. Oh, look, I didn't even notice on this first one initially that they have two different y's, because I don't care. If there's a list of ordered pairs, I don't care, right? If the y's are different, every x must go to a different y. So negative 2 goes to 4. Also 3 goes to 4. That's okay. What's not okay is this situation down here where 1 maps to 1 and also to 2. Right? Now, when we're listing our coordinates, I don't have to list those 4's twice. All I'm saying is the range has a 2 and a 4. I don't need to say, hey, it has a 2 and a 4 and a 4. Right? So same thing here. When I'm listing the domain of this relation, because it's not a function, I just need to list that 1. I'm saying, hey, there's a 1 in the domain. Doesn't matter if it goes to 3 different y's, and then there's a 2. Okay, the range for this one is there's a 1, a 2, a 3. The domain for this one then would be what? Right, negative 4 and negative 2. And the range for this one would be what? 1, 0. Okay, so if I've got a list of ordered pairs and I'm trying to determine if it's a function or not, all I need to do is look at the x values. As long as they're all different, it's going to be a function. And it really doesn't matter what my ordered pairs are represented as. Look at this. I've got my x values with some kind of mapping over here. So this means I could just rewrite this as, oh, that's the point 1, 2. This is the point -2, 4. This is the point 3, 4. Right? It's the same thing, just a different way to represent my ordered pairs here. So all I'm looking for, again, are my x values. Look, they only have one line leading out from each one. Each x is different. So yes, this is a function. Let's look over here. Whoops. Look at this. This -2 is mapped to a 1 and to a 0. No, not a function. Okay, so what's the domain of this one? 1, -2, 3. And what's the domain? The range of this one? That's the y value, so 2, 4. Right. Okay, the domain of this one is -4, -2, and the range is 1, 0. Excuse me. Okay, so that's how to tell if something is a function when we have basically a set of ordered pairs. If I'm looking at the graph, I have something called the vertical line test. Vertical line test. I just need to draw a vertical line anywhere on the graph. And if I can draw a vertical line, imagine these are straight and vertical, anywhere, and it crosses that graph more than one time, then it's not a function. Now notice that's telling me the same thing as a function. Here's my x values. So if I go along here to my x value, this x value, oh, here's one y, and here's another y going to that same x value. That's why the vertical line test tells us if it is or is not a function. So this thing's not a function. Let's talk about the domain and range. Remember, domain are our x values, range are our y values. So if I want to, I'm going to switch so that I have that blue's too close to these blues. So if I'm talking about the domain, I'm talking about, okay, all the x values, right, from here to here. Where are there x values for this graph? Well, there's not any over here. None, no x values when I look up until I get right here. When I get right here, there starts being x values. For this x, there's a value. For this x, there's a value of the function. For this x, there's a value. So 1, 2, 3, 4. So from -4 all the way over to +4, there are x values. And then out here, there's not any graph, there's not any graph, there's not any graph. So my domain, now remember our interval notation, we're going to use interval notation to do this. So my domain is going to be anything from -4 to 4. And again, I don't want to just list my numbers, -4, -3, -2, because there's also a value right here for my graph, you know, right here associated with this x value. So I need to do it in interval notation. Range is asking about the y's, so it's the same process, except I'm looking for my y values, right? All of these are my y values. So if I'm coming up, there's no graph until I get to 1, 2, 3, 4, 5, 6, -6. And then there's graph all the way across until I get up to +6. So my range is -6 to +6. And remember, no, it was not a function. That vertical line test failed. Okay, what about this one? Vertical line test. There's nowhere that I can cross that with a vertical line, and it crosses it twice. So yes, this is a function. Okay, now domain and range. Domain, my x's, I'm looking across here, right? Looking across here. So there's no graph, no graph, no graph. I'm thinking, but hey, when I pay attention to this graph, I notice there are arrows. That means really this line, right, is extended. Come on, line, extended forever. So yes, there are values here. There are values forever. Anytime you run across, if your first piece of the graph you run across has an arrow, then if it's the first one, you're talking about negative infinity because it's going forever this direction, right? It's going forever in this x direction. So negative infinity. And then there's graph, 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 graph. Same thing here. There's an arrow, meaning it continues forever. Okay. And then I'm going to do the same thing for the range. So what do you think the range is? The y values, and you're right. When I go up the y, and go from negative to positive, right? So you get your interval correct. When I go up the y, because that arrow means it's extended forever, as soon as I see an arrow, all right, then I know it's going down, down forever to negative infinity. And the same thing, the last thing I see is an arrow, meaning it's going up forever to positive infinity. Okay, what about this one? Let's see, do your vertical line test. I'm not going to physically draw them, but think about this, vertical line test. So yes, it is a function, right? I cannot cross that graph more than one time if I draw a vertical line. Domain. Domain are my x values. So I'm coming across, looking, for the graph. The first piece of the graph I see is an arrow. Okay, so that means it's going all the way to negative. It's going this direction, slightly just over. As it goes up, it goes, this direction forever. And then I'm going across, and there's graph, 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 graph. And the last piece of the graph I see is an arrow. Once again, indicating not only is it going up forever, but it's, veering this way forever to where the x is infinity. Range. I'm going up, no graph, no graph, no graph, no graph. Oh, here's the first piece of the graph. When y is -3, now I'm going to include that point because it is touching that -3 point, right? And then there's graph, 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 arrows, meaning it's going up forever, so it goes all the way to infinity. Okay? So on graphs, determining if it is a function, use the vertical line test. And then how to find the domain and range from the graph. All right. What if we had an equation? How do I know if it's a function? So first let's go determine if they're all functions, and then we'll talk about the domain and range. So if I have an equation, notice I keep saying equation. I'm going to get this one out of the way first off because I don't even know why it's in here. If you have one, and you'll have one on your homework, that has an inequality, then it's not a function, right? These are not ever going to be functions because we have a less than. There's a ton of x's that go to y's, and your domain and range is going to be negative infinity to infinity. So, and then I'm not going to worry about this anymore. So just put that as your answer, and we won't be concerned with that. I don't even know why that's a question. Okay. All right, but the other ones, if I have equations and I'm trying to determine if they're a function, okay, then I look at the y value. If I had a list of ordered points, I look at the x value. If I have a function, I look at the y value. Okay, so as long as the y does not have an even exponent or absolute value bars or anything that makes a positive and a negative y the same, notice how that's telling me the same thing as what is a function. Hey, if this x is 9, if I've got a y squared, this could be 3 or negative 3. I've got one x going to two y's, right? So I can't have anything on my y value that makes two different numbers equal the same value. So even exponents, absolute value bars, that's the kind of things that I'm looking for there. So right away, then we know that this one is not a function. And if I look at this, that's just a y, that's just a y, that's just a y. All the others are functions. See, notice that most things are functions. Now you'll also notice, let's think a minute about those graphs. The reason we did circles already, because they're not a function. That's why we just kind of threw circles in. Hey, here's an equation. You know, most equations are functions. So circle is not a function. So we talked about it before we started discussing functions for the rest of the semester. Okay, so linear equations are functions, radical equations are functions, rational equations are functions, right? Now notice we've talked about how to solve all of these before when they had one variable, before they were functions and just equations. We talked about linear I told you need to know about linear equations. I'm going to tell you the same thing about linear functions, okay? And then we talked about just radical equations when I had numbers over here, one variable. Rational equations where I had numbers over here. Actually, thinking about this, I'm going to add an equation to this. How about an aquatic? Not a quadratic. I don't know where that came from. How about a quadratic equation, right? Because we've talked about solving them also when we only had x's. But now, notice, I don't care if that x is squared, right? It's the y I'm interested in. So yes, that one is also a function. Okay, so telling if they're functions, really easy. Just look at the y value. Domain and range. Okay, so domain and range. The domain and range is always going to be negative infinity to infinity, except under two situations. Okay, and it's the two times when we had equations we had to check our answers, because that's times when, we might have a problem. Okay, so those two times are if you have a variable in a denominator, because denominators cannot be zero, or if you have a variable underneath a radical, because if we want to stay in the real numbers and not consider complex numbers, you can't take the square root of negative numbers, right? Okay, so everything else, as soon as we see, is this a function? Yeah, it is. Oh, well then, as long as I don't have a variable in a denominator or under a radical, my domain and range are all real numbers, right? Which is negative infinity to infinity. Don't know why I put a bracket there. Okay, so domain and range, all real numbers. On this one, and on this one, all real numbers. This one's not a function, so we got to deal with it differently. And this one has a variable in the denominator, and this one has a variable under a radical. So I got to think this process through. Okay, so my problem here is denominators cannot be zero. All right, domain, remember, means x's. Domain means x's. So I'm asking myself, is there anything that x cannot be? Yes, it cannot make a denominator zero. So if I solve this equation, right here, I find out that x cannot be 1. because 1 would make the denominator 0. It can be anything else. It can't be 1. You can't have a denominator that's 0. So my domain, we're going to write this as, oh, well, let's say it's negative infinity all the way to 1, but don't include 1. Remember what that parenthesis means. Or start back at 1 without including it and go all the way to infinity. Okay, remember our interval notation there? So this is negative infinity all the way to infinity, except take out 1. All right, now, since there's a problem with the domain, I got to think about the range. Is there any number that this fraction cannot be? Can this fraction be and here's the thing, I'm always talking about, can it be negative? Can it be 0? Can it be positive? Right? That's always the things we're thinking about. And the denominator cannot be 0. Okay, so can this fraction be negative? Oh, yeah. Let's put a number in here, 0. Then we've got 5 over negative 1. Yeah, this can be a negative number. Can be lots of negative numbers. Can it be 0? What makes a fraction equal to 0? What makes a fraction equal to 0? The only way a fraction can equal 0 is if the numerator is 0. I can't change that numerator. That numerator is going to be 5. It's going to be 5 divided by something. It can never be 0. All right, so right away, I've got that taken out. Now, can this fraction be positive? Oh yeah, as long as I put a number here, like 3 minus 1 is 2, then 5 over 2, it's positive. So my range, come on. Well, I guess that doesn't matter, but so my range is anything but 0. So any other numbers is okay. It can be all kinds of negative numbers and positive numbers, but it can't be 0. Now, if this had an x up here, if it was 5x, oh, then it's possible we could make that 0, right? By plugging in a 0, and you'd have 0 over negative 1, which is 0. The only reason I'm saying this fraction as it stands can't be 0 is because the numerator is 5, and there's no variable or no way up there to change it to 0. Okay, domain for this one. So our problem with radicals is we know that whatever's underneath here has to be greater than or equal to 0. You can't take the square root of negative numbers if you're talking about real number solutions being the only thing that we're going to accept, right? And that's what we're doing. So it's got to be greater than or equal to 0. So if I solve this little inequality for x, I find out that x has to be greater than or equal to 1/2, right? So the way I write that in interval notation is greater than or equal to 1/2. It can be 1/2. So I'm going to start with 1/2, and I'm going to go all the way to infinity. Greater than or equal to 1/2. That just came from solving that equation under the radical. Every time it's a radical, I just set what's underneath there, greater than or equal to 0, solve it, and then that's how I get my interval. Now, let's think about the range. I'm always asking myself, is it possible for the y's to be negative, for them to be 0, for them to be positive? Right? Think about the number line. That's the 3 sections. Okay, so can I take the square root of anything and get a negative number? Nope, can't do it. Can't get a negative number there. So negatives are out. Can I take the square root of anything and get 0? Yeah, if that equal to 0 in there. Can I take the square root of anything and get a positive number? Oh yeah, square roots are always positive. So this starts with 0 and goes to infinity. Okay, hopefully that was okay. It'll take some practice. Let me know. All right, I'm going to get rid of all this while we talk about this non-function. And we're going to get a little more practice, because when it's not a function, I have to do the exact same thing on x and y, right? On x and y. So I'm going to ask myself, for the domain, is there any way that this x could ever be, remember what we had, negative, 0, positive, can be negative? Oh, when you square something, can you ever equal a negative number? Nope. Negatives are out. Is there any way you can square something and have it equal 0? Oh yeah, if you're squaring 0. Is there any way you can square something and have it positive? Oh yeah, everything. So notice this is 0 to infinity also. Range, same question, except range, we're applying that to y's. Okay, so is there any way that I can square a negative number? Yes. Can I square 0? Yes. Can I square a positive number? Yeah. Yeah, I don't have a problem squaring any of those. The range, that y, can be any number I want to plug in, positive, negative, 0. But when I plug them in, I will never get negative numbers on my x values. All right, so a thought process. Okay, so just to sum that up, right? For ordered pairs, remember, look at the x value. Your x's must all be different. For equations, look at the y value. They can't have an even exponent, absolute value bars, anything like that. And for a graph, just use the vertical line test. All right. Now that we can determine if something is or is not a function, we have a special notation to indicate that, hey, we're dealing with a function. So if I see this notation, I don't have to think about, is it a function? It's telling me that it is a function. Okay, so here's my function notation. It's f of x. It's not f times x, it's read f of x, right? F of x. And y is f of x. So y and f of x are just completely interchangeable. Well, hold on a minute. If it's a function, y and f of x are completely interchangeable, okay? Immediately, if I see f of x, I can exchange it with y because I know it's a function. If I see a y, I need to make sure it's a function before I replace it with f of x. But y and f of x are the same thing. It's just, this is just going to be a shorthand notation for us. So look at this. Here's a function because it's an equation. I look at my y value. It doesn't have an even exponent or absolute value bar, so I can immediately change it to f of x is 3x minus 5. And the shorthand notation is, you might be saying, that's a little bit longer. Well, it's, if we're using this, if I wanted you to tell me what y is for this equation when x is 2, I'd have to say all those words. You know, evaluate this equation when x is 2. That's about as short as it gets. And we all know, oh, all that means is, oh, if x is 2, then plug in a 2 for x and simplify it. Okay, so y is 1 when x is 2. With function notation, all I need to say is find f of 2. Okay, and that'd be written like this, f of 2. That means let x be 2. Same thing we did over here. So then when we solve it when x is 2 and we find out it's 1, I can write it like this. I can write f of 2 as 1. And that tells me, oh, when x is 2, y, because f of x is 1. So when I have this notation written like this, it tells me a whole lot. And I can also give instructions easily. Find f of 4. Oh, that means plug a 4 in. All right, so we're going to practice that. That's our function notation. Okay, what do we have here? What is that crazy thing there? Okay, I think all of this accidentally got left in. Okay, so let's ignore all of this, and that's crazy anyhow. I don't even know what. Okay, I guess they're just explaining what I just did there, f of 2. Okay, so let's go to our next examples. Oh, wait, better erase that. Or look, this is why I have to go over and erase it every time, guys. If I don't erase it, that'll just stay on my next slide. Okay, so let me erase that. Come on, come on. Okay. All right. So let f of x equal negative x squared plus 5x minus 3. So I know it's a function. And here I've got g of x, so I know it's another function. By the way, yeah, look, same notation. If we have more than one, we don't want to call them both f of x because they're different functions. So you can have f of x, g of x, h of x, you know, whatever you need. The basic one starts with an f for a function, but if you need more notation, just like if we need more variables, we can use x, y, z. So find each of the following. F of 2. So first of all, under this situation, I got to pick the right function. Right? Notice this one wants me to plug in to this function, but this one wants me to plug into this function. So pay attention to that. So f of 2, it simply means we'll take that function f, and everywhere there's an x, right? Everywhere there's an x, put a 2. So I'm going to have negative 2 squared plus 5 times 2 minus 3, and then evaluate it. Now, be very careful with your negative signs. This negative has nothing to do with that x. Remember, if it did, it would look like this. So this is negative, and then 2 squared is 4, plus 10 minus 3. So f of 2 is 10 minus 7, or 3. F of 2 is 3. When x is 2, y is 3. When x is 2, y is 3. We can also plug in other expressions. It doesn't have to be a numerical number. I can plug an expression in. So for g, if I want to find g of a plus 1, all that means is plug a plus 1 in everywhere there's an x. Instead of x, replace it with a plus 1. So 2, but instead of x, a plus 1 plus 3. Okay. Now, I'm not going to get a numeral, but I can simplify that and have 2a plus 2 plus 3, or g of a plus 1 is 2a plus 5. F of q, okay? So f of q is asking me to do what? Yep, replace every x with a q. So negative, whoops, let's get our equal sign in there. So negative q squared plus 5q minus 3. And I can't simplify that any further. So that's it. Okay, so using function notation. It's really simple. Okay, some more using function notation. For each function, find f of 3. Okay, notice they've called both of these f. Okay, I get because it's two separate problems, right? That other one was one problem. Let f be this and g be that. Okay, but now this is like, here's a problem, here's a problem. So f of 3, once again, f of 3 means you just replace the x with a 3. So you wind up with 3 times 3 minus 7, or 9 minus 7, or 2. So f of 3 is 2. When x is 3, f of x, y is 2. So over here, f of 3 means, remember, x is 3. So let's see when x is 3. Here's where x is 3. So when x is 3, y is 1. Okay. Let's see. Same thing. Find f of 3. So let's do it for this function. F of 3. When x is 3, I'm sorry, didn't mean to point at that when I said x. When x is 3, here's my x is 3. Oh, y is 5. Okay, let's look over here. When x is 3, x is 3. They're kind of telling us this answer here. Y is 4, right? When x is 3, that's on my line. When x is 3, y is 4. Okay, writing equations using function notation. All right, well, like I said, once we figure out it's a function, I can just replace that y with f of x. So when I look at this, it's a function. I can just write it f of x equals x squared plus 1. Then find f of 2. Okay, so plug it at 2 everywhere there's an x. So f of 2 equals 4 plus 1, or f of 2 equals 5. So there's f of 2, and there's function notation. Now I can tell this is a function because when I look at my y, but I probably don't want to put my f of x in here until I solve it for y. By the way, whenever I use the f of x notation, it needs to be all by itself. I'm not going to put the f of x notation in the middle of my equation, right? Solve it for y first, right? If this was a y squared, I wouldn't need to just say it's not a function. I don't have to solve it for y, blah, blah, blah. But once I recognize, oh, I can tell easily it is a function, but before I replace that notation, I need to have it solved for y. So if I'm trying to get the y all by itself, right, we're going to subtract x from both sides. So we have negative 4y equals 5 minus x. I'm going to put negative x plus 5. We usually put the variable first. It doesn't really matter. Then I'm going to divide everything by negative 4. You can do this individually, or you can do it all at once. So you could either do it like this, or if you had this, like we were, you could say, okay, as long as you divide everything by that negative 4, either one of these, right? Either one of these. Now, this one will simplify and give you y equals, you would have a positive x over 4 and a negative 5/4. That's fine if you prefer that. And then you replace f of x equals x over 4 minus 5/4. Or if you preferred this, right, that's still going to cancel. And you have y equals negative x plus 5 over negative 4. And now I can replace that with f of x equals negative x plus 5 over negative 4. And either one of those is fine. Now let's find f of, oh, we didn't do negative 2 on this one. I just did f of 2. All right, so be aware of that. Okay, so now let's do f of negative 2. F of negative 2 is negative. Now x is negative itself, so don't forget I need both of those. My x is going to be negative 2, but I already have a negative out there. plus 5 over negative 4. So f of negative 2 equals positive 2 plus 5, 7 over negative 4, negative 4/7. Which notice if I put a negative 2 in right here, that's what I'd get, negative 7/4, right? Negative 7/4, putting it together with that common denominator. So just be aware, I'm not going to go back and do this one with negative 2, right? Actually, it'd be the same answer because maybe I should talk about that. If I put an x in for negative 2, that whole thing would be squared, right? And be 4 anyhow. But be careful of those signs, careful of those signs. Okay, last thing we're going to talk about from this section is when our functions are increasing, decreasing, or constant. So what do those words mean? Increasing, decreasing, constant. Right, increasing is going up. If something's decreasing, it's going down, and constant means it's not changing. Okay, so it's pretty easy to see that this function is decreasing right here. It's increasing right here, and it's constant right here, right? So this is decreasing, this is increasing, and this is constant. But the tricky part is most people want to say, I kind of hate to even say this, but they'll say something like, oh, it's decreasing from negative infinity all the way down to negative 1. No. We say the function is decreasing when x goes from here to here. All right? So the function is decreasing when x goes to right there. Right there. And then it's decreasing. So I've got an arrow. So that means negative infinity. It's decreasing when x, right? When x is negative infinity, all the way to when x is negative 2. When we're doing increasing and decreasing and constant, everything gets a parenthesis. Because I can't include negative 2 and say, hey, it's decreasing at negative 2. Well, it's also increasing at negative 2. That's where it changes. It changes from decreasing to increasing. So I don't include that point in either piece. I just say until negative 2. And then at negative 2, it's neither increasing or decreasing. It's changing, right? All right. So now if I want to know when is it increasing, it's increasing when x goes from negative 2, I wish I could draw a straight line for you guys. When x goes from negative 2 to negative 1, this interval right here is when this function is increasing, right? The function is increasing, so the y is remember, you can replace function with y. The y is increasing when x goes from negative 2 to positive 1. And then the function is constant. Y is constant when x is from 1 all the way to infinity. Okay, I hope that made sense. We're going to do another one. Excuse me. Okay. Same thing. Increasing, decreasing, and constant. So increasing, this function is increasing right here. But don't forget, that is saying y is increasing. It's not saying what is y increasing to. It's saying when is y increasing. Oh, y is increasing when x is 0 to 25. Well, when is it decreasing? Oh, it's decreasing when x is 50 to 75, right? It's decreasing right here. So that's when x is 50 to 75. Increasing, decreasing, or constant. When is it constant? Oh, it's constant right here when x is 25 to 50. Or, right? Or it's also decreasing when x is 75 to 100. So increasing, decreasing, constant. Sometimes it's hard to keep track that we're looking at the x's, instead of the y values, but that's the trick part of that. If we get that down, these are really easy too. Okay, so one comment for you. Just like when we started solving equations at the beginning of the course, and we skipped linear equations and said you should already know how to do that, we're also going to skip linear functions, right? So a linear function are those kinds like this. Also, you notice now that we have x's and y's, eventually we're going to be graphing these things, right? That's where we're headed. So solving and or graphing. So we're not going to discuss linear functions just like we did in linear equations. There is, if you need help with that, if you need practice, you let me know and I'll help you through it, of course. And there's homework, optional homework. You don't have to do that section. I think it's 2.4, 2.5. 2.4 or 2.5. Anyhow, it says optional on there. Doesn't count against your grade if you don't do it. So if you already know how to graph these linear functions, you're good. If you don't, you might want to do that extra work there and get some help with that from me, tutor.com, wherever you get your help from. Okay, I'll see you guys next time. Let me know if you need anything.